just click there?
Yes.
Okay.
I can.
Okay, so thanks for introducing me. So, yeah, my name is Mandy Bethkenhagen. I'm working with Redmer at the University of Rostock in Germany. And I've also been working a lot with Sebastian Hamel lately on the Superionic water-ammonia mixtures. So basically, most of the work I'm going to present here has been done during my time in Livermore. Okay, great. So what am I going to talk about? So actually, I'm also talking about stuff which had been discussed in the talk before. So I want to talk about superionic phases in particular, and I've been focusing on water ammonia. So I'm going to discuss the superionic layer, which is not just composed of water, but also water ammonia. So just to actually question this important question here. So water ammonia, why is that even important? As we heard like in the previous talks, water is very abundant in our solar system, and the planets should be just be composed in large fractions by water. But where do we actually find ammonia in this system? So if we have a look at the moons in our solar system, there are actually lots of moons. So it's 165 moons in total for the gas giant planets. And lots of them, for example, like Europa and Titan, have something like water oceans in there or water ammonia oceans. So for example, if we have a look at Titan, the most recent model here on the left-hand side, which had been done by Frank Sohl and Frank Wagner from the DLR in Berlin. They are discussing this layered system here for Titan. So for example, you have an icy crust made out of water outside here. Then you have a water ammonia ocean, which is liquid. And then you have high pressure ices in here. So actually you find in this system a real water ammonia ocean, which is really interesting. But when, again, if we have a look at the pressures are only up to 100 kilobars, which is like 10 GPa. So this is not the state I'm actually mostly interested about. I want to do systems which have a bit higher pressure. So we have a look at Uranus and Neptune again. And as was already claimed, like in the previous talk, oh, there's superionic in there. Actually, I just want to point out there's a paper by Solarlund and Hamel, and they also said that the whole interior can be convective, and they can also find magneto-hydrodynamic models which are matching. So actually, it's possible to make a magnetic field with an interior which is not completely, which is completely convective. Just to inform you about that. So, but still, we still have this problem for Uranus and Neptune here, that we don't really fully understand the magnetic field in relation to the interior and also the evolution of the planets. So what could be a possible explanation? And I just want to point you to the middle of this view graph, because this model here for Uranus is actually the first one which totally matches all the observational constraints for the interior structure, which is completely made out of here in the interior of water, ammonia, and methane. And all of the three equations of state are completely ab initio. So this model here had been done by Nadine Mettelmann and is unpublished so far. So, but to still understand the connection to the magnetic field and also the evolution, which is still a problem even in this model here, we wanted to have a look what happens to the superionic phase if we add some ammonia in there. So just a quick reminder, what is a superionic phase? So superionics for the planetary applications had been first predicted by Cavazzoni in 1999. And what I want to see when I talk about a superionic, of course, it has to be a charged system. And if I look for something like a water ammonia superionic, I have to have a fixed lattice of nitrogen and oxygen ions, and then have to have hydrogen ions diffusing through there. So what's like the current status of the research on water and ammonia? So water, we already had seen this view graph here before in the previous talk, and also the ammonia one. And what is interesting about it, if you have a look at the isotopes of Uranus and Neptune, for the water case, they clearly go through the superionic phase, while in the ammonia case, they just they scratch around the superionic phase. So actually, we always concluded, okay, so ammonia seems not to be important. But what happens now if we look at the mixture? That was the main idea behind this idea. I just want to also point you to the fact that it's also predicted by Burkhard Militzer's group. This is work been done by Wilson in 2013, that is also predicted like phase transitions within the superionics. So that's also something to note. So what have we done? So I guess most of the people here are familiar with the calculation. So we employed our old working horse VASP. So basically we do this molecular dynamic simulations when with DFT on top for every ionic time step. And we just use in that case here the PBE functional and as the Monca's PEC k-point set, for example. Okay, but what is new about these calculations? Since we did some random structure searching, we wanted to see whether we can actually find some structures which can later, when upon heating, be shown to be superionic. And so we did at 1, 2, and 5 megabar extensive structure search and found some structures. So this is like the main summary for the structures I found. So at low pressures we find the P4NMM phase, which is shown here, and this had been previously predicted by the group around Griffiths and also with like the help of Chris Pickard. So what you see here is like you have this layered system of ammonium ions and then OH ions there, and but when we increase the pressure, this transitions to the IMA2 phase, then the PMA2, and then the PM phase. So these values here for the transition pressures are actually the dashed curves. And as Miguel Morales pointed out this morning, in this pressure regime it's very important to have zero-point motion energies. So we also did some phonon calculations to account for that. And you see the transition pressures change quite significantly, up to 14%. So it's really important to consider the phonons here. So the structures I'm discussing actually look like that, and if you have a close look at all of the structures, you notice that they're basically decomposed into subsystems. So we always find these OH bonds with ammonium ions for one group. So this is shown here for the P4NMM and the IMA2. And then as the pressure increases, actually the bonds are symmetrizing. So what you see then is you have these OH-O chains here, and also for the PM, just the angle basically changes, but we still have the symmetrized bonds, which was also described in water systems before. So if we, for example, have a look at the OH bonding length, this is shown here for the different structures, you actually see there's like the P4NMM, which has like the other two curves here with normal behavior. As you increase the pressure, the OH bond shrinks. But then the IM2 structure has this funny behavior that the OH bond actually increases a bit. This is due to the change because this IMA2 phase is changing from this OH bonding to the actually chaining. So this is kind of a linking structure. And then what we did was we heated all the structures we found for the low enthalpy. And we always saw that the hydrogen ions are diffusing. So we basically subdivided them here in two groups, hydrogen ions which were closest to nitrogens and hydrogen ions closest to an oxygen. And what we saw, so we couldn't find any significant hints that the subsystems are melting with a different temperature or something. It's just they are both starting to diffuse at the same time. And also what's shown here is the lattice was fixed throughout the whole simulation. So coming now to the phase diagram we're predicting. So we have these four solid structures here. And what was really surprising, given when you have a look at the Neptune and the Uranus isotopes here, actually the superionic region is far more extended than it would be for just ammonia. So if we have a look at the comparison to the previously published data for water and ammonia itself, so the blue dots are always ammonia points where ammonia is superionic, and then the red dots are where water is superionic, and then there are these calculations by Wilson, so they directly determined the actual melting line of this, and also this phase transition line here, by employing the Gibbs free energy evaluation. And what you see here, actually, what's interesting, well, if you compare this Superionic region, it starts pretty low, almost as low as for ammonia, and it's far more extended than it would be for real ammonia. So, in principle, if you have a look, Neptune and Uranus are almost completely Superionic now in the inner mantle, if you consider this mixture. So to just quickly summarize, our results actually hint to that we should be thinking about the Superionic not just be composed of a pure compound, but of a mixture. So actually, we should consider water-ammonia mixtures in there. And what's really interesting and left to consider is, so what's happening if we, for example, add different molecules now, like methane. For example, that kind of calculations are done by Ed Meyer, also here, and he has a poster on Wednesday, so if you're interested, please see his poster. And so is there, and also the question if there's just one Superionic phase in these planets. So for example, you could think of just having a water Superionic and then a water ammonia one, or is like there are also like some different phases, is there a phase transition as it was predicted for water. So with this, I really like to thank you, and if you can't remember anything from my talk, please just remember this. I'm doing ISIS for hopefully the interior of the planets. So thank you.
Any question for Mandy?
Nitrogen is 6 times less abundant than oxygen. Do you have any understanding at all of the effect of that?
Oh, I mean, I just considered a one-to-one mixture here, which is really extreme. I'm totally aware of this, but I just wanted to get a significant effect, right? But we're actually looking into this now. We're now also changing the concentration to account for that. So it probably will shift the whole Superionic again a bit, but we just wanted a principal understanding of that. So actually, I mean, we already did like some first trial calculations to put in something and see if the Superionic is still stable, but it's really hard to tell yet what's going to be the result there. And actually, what I figured during my calculations is actually you can start with as bad of a lattice if you want. For example, I really started with a really just normal FCC lattice, and it already had the Superionic behavior. It was just that the lattice positions for the heavy ions were just not right.